the idea behind today is to really do a high-level explanation of commercial irrigation from specification and design through to the installation process, and then handing it over to, you know, whether or not it's councils, schools, golf courses, private clients. Obviously, you guys work for all of those different customers. And so you'll see there I've got a list of tools. Irrigation is one of those things that can really easily be started by someone with a car and pretty much a set of cutters and a set of multi-grips. That brings with it risks. Obviously, people that you know, can start a business for $40 may not necessarily have all the qualifications required to do the work, and then you know, it goes out from there. So there's a list of tools there, which for some of you you wouldn't have seen that before, and for some of you you've probably seen it, and you have all these tools available to you. I wanted to put it there just to highlight the simple nature of what is available, but then also how advanced it can get. You'll notice that there's earth ground resistance testing kits. Our team would use them to test the wiring on a decoder system to ensure that the grounding has been installed properly. It's not something that is done very much, and as I was saying to the guys at the back when they got here, what we're starting to see now from councils is an expectation that the earth grounding resistant tests are being done and handed back to council to prove that your wire joins and your decoders are actually grounded correctly and that they're actually working. I'll explain decoder controllers and wiring further in for those of you that are probably wondering what am I talking about. There's just a few kind of like small differences between, you know, you've all got drills, but do you have long drill bits? Obviously, if you're going to be doing maintenance on irrigation systems, you're trying to get into a valve box to take a valve apart, you're going to benefit from having a longer drill bit. You'll see there things like leg rammers. As we go into the specifications of irrigation, I'll explain why. And then, you know, alcohol wipes, electrofusion welders, we've got them here. I'm not going to spend any time on how to electrofusion weld. That's a whole separate thing. But just really to highlight almost, you know, the basket of tools that you could use and that you may use to do irrigation installs is not that broad. The next thing you'll see there is licensing. As with a lot of things, licensing in irrigation is really not keeping up with irrigation itself, and there are licensing requirements that are changing all the time. Obviously, the burden of licensing is going to fall with your managers and your owners, I'm guessing, but I think it's important for you to know that there are licensing requirements around irrigation and landscaping. I'm actually on the board for the Master Landscapers Association, and it's something that we spend time on trying to improve the way that that's managed, make it easier, not necessarily easier to get a license, but easier to understand the pathway to getting a license. And there's a few links there. Obviously, the Consumer and Business Affairs take care of the licensing, but I've got a link there from a guy who runs a business called SA Trade Licensing. If any of you are looking to try and get help to get licensing, he used to work for the Office of Consumer and Business Affairs. He understands the hoops that you have to jump through and the hurdles that you have to jump over to get your licensing, and he can actually help you go through that process, obviously for a fee. We don't have any financial connection to him. He's just a good dude that I would recommend and I would use if I needed a license. So let's get into the actual, I guess, meat of it all. So commercially, the majority of the projects that you guys are likely to be working on will have some form of specification. And obviously, if you're working for a council, the specification is going to be quite robust. Obviously, depending on the council, some councils have, you know, a loose 4-pager that they've copied from someone. You're getting me a spec. I know that you guys at the back have definitely worked for Playford Council, and you'd be quite across their specification. I'm a big advocate for specifications and then obviously irrigation designs with the view of having systems going in well, but also making it fair and competitive for landscape companies when they're going to quote these jobs. Because obviously, if there's no specification and there's no design, it kind of leaves it open for a rogue landscape company to come in and do a very cheap bid, obviously not meeting any accepted standard, and then obviously it's quite easy for them to win the job, but then obviously the job doesn't meet minimum standards, and we've seen that happen and then obviously the council will choose the cheapest bid. Council gets pissed off that the job's shit, and then the council wonder why the job's shit, and this kind of circle of that. But we've got a copy of Playford's spec here, which I'll pass around so that any of you that haven't seen it can see it. I use them as an example because I think they're probably one of the most detailed specs, and they're a council that actually reinforces their spec. We're starting to see it more and more with councils like Adelaide, Onkaparinga, Playford obviously, but then there's other councils that kind of have a very loose spec that they don't require you to adhere to, and then you can kind of get away with stuff. And I think that what we're starting to see is not only more councils are actually having a written spec, they're actually reinforcing their spec, and we're actually having conversations with councils now about us doing an audit on a job upon completion. So there could be jobs where the job gets specified, the job gets designed, you tender for it, your company wins it, you purchase the goods, you install it. Usually that's the end. And there might be some hold points through that process where someone like Waterpro or another consultant might come out and check things and go, yep, they've done that right, the wire joining's done right, etc. Then they're going to go to the next step where it'll be written into the tender that if you don't meet a certain distribution uniformity from your sprinklers, or you don't pass your resistance tests on your decoder systems, that they'll require you to fix or I guess adjust things to make that right before you get paid for the job. So I think that sometimes people can get a little bit caught up in thinking, well, this specification stuff's kind of shit. Like, why is it that important? There's so much in there about micro detail. It's really, like I said, designed to protect the council from the work. Have you got a stapler or a clip or something? Just so I can hand it around. It's not just to protect the council, it's also to protect you. So if you've got a written spec as the contractor, even if you're working underneath a team, you don't have to go back and ask questions, and you might find that you're embarrassed to go check again, or you know you've been taught how to do it, but you don't want to ask again. A lot of the requirements are written in these documents that you can refer to, but you can also protect yourself when the council come out and say you've done this wrong, and you're like, well, I don't think I have. I've done it in line with this written specification, and they're like, huh, okay, yeah, you're right. You've done it right. So we use these written specifications as not a guide, as a rule book for how to design irrigation systems. And then we design the irrigation system, obviously, off the back of that. Do you want to just pass that around to anyone that hasn't seen it, just so they've got an idea? If you are working for a council, I encourage you to make sure that you stay abreast of the version of the specification that they're currently using. Playford are on version 2 point something, and I think they've got a 3 that they're working on at the moment. You can get, obviously, as irrigation technology evolves, then the specifications evolve. And if you've got one that's been in the glove box of the ute for the last 4 years and you've almost memorized it because you're doing so much work, say, in the Playford Council, you could be at risk of installing something that's kind of not how they do it anymore, which could cost you more because they've reduced the amount of parts required, etc. From a specification standpoint, if there is no specification on a job, I would encourage you as a business to kind of have an understanding of what your business's minimums are. And that could be something that your irrigation team could work on around, we only use this brand of valves, or we only use this brand of cable, or we only use this brand of PVC, or we only, if we're doing an oval, our ring main, so the pipe that goes around the oval has to be electrofusion welded blue line, or whatever it might be. And I think the advantage of doing that from a business standpoint is that your team will start to learn what the parts are, so that when you're doing maintenance on those parts, you've got really less parts to carry, but you've also got less training to do as you've got new staff come in, obviously. So we take those specifications, and you probably are aware if you flipped over to the page, we have a design team, one of them sitting right here. He's not on here yet because we don't have a photo of him, I don't think. A big part of our business now is irrigation design and irrigation consultancy. We've got a 4-person team based at Kent Town who would take a specification like that Playford spec, and then we can go do GPS plotting of an area, and then get that into the computer and design an irrigation system, which obviously then goes out to tender potentially, or in some cases we're doing designs to be built. So for the guys here that have done irrigation, you'd be doing a lot of D&C, so design and construct, or you've got that kind of hybrid of working on existing designs. The design and construct game is almost as risky as the non-specification game, because if Waterpro might design an irrigation this way, and then one of our competitors do it this way, And it doesn't necessarily mean either of us are right or wrong. It's kind of an art mixed with a science. So when you're putting sprinklers on an oval, 3 different designers will do it 3 different ways, and you can sometimes be criticised, and we would get criticised for our designs from other designers, and we would criticise other designers because of their designs. It doesn't mean, well, sometimes it means they're wrong, but it doesn't always mean they're wrong. It could mean that they've just done it differently, and they've taken different information into account when they're doing the design that the other people haven't taken into account. It could be around experiences with sprinklers, pressure and flow that's not available, that, you know, we know the pressure and flow in some suburbs better than most. Like, we do a lot of work in Playford. I keep referring to Playford. So we know that we can't add an extra valve onto a certain thing, so we might design it differently. So the design teams there, they will also be the team that would be going out and doing audits on systems. It's going to be interesting for us. Obviously, we are a supplier and a designer. And I think it's going to be a big challenge for us when we have to start auditing systems for customers that we've supplied, because we're obviously trying to maintain a good relationship with our customers, but also then kind of tell them that maybe they might have done that wire joint a little bit wrong. So that'll be an issue we'll have to deal with. I'm guessing our customers will hate our design team and they'll love our salespeople. I don't know how it's going to work, but you'll see there's a bit of information around design. Like with anything, the better the quality information we get around a design, the better quality information you're going to get back as a contractor on the design. What else we got there? Backflow. You've probably seen backflow prevention devices. I'm not sure how aware everyone is on them. It is a state government regulation for irrigation systems to have backflow prevention in place. I'm on the bottom of page 5 at the moment. We're still seeing situations where there's cross connections between drinking fountains and recycled water, and the reason that it's so important for us to do irrigation designs is to avoid that happening. And there's still jobs that go ahead where to save money, the contractor might just run one single main line that is designed to run the irrigation system and the toilets and the drinking fountain, and all of a sudden you've got a cross connection where you can imagine, you know, one of your family members or you are drinking water that's, you know, there's no backflow prevention stopping water from coming back from a toilet into a drink fountain, or from a sprinkler that's got chemicals being sprayed onto the lawn back into your drinking fountain. So I put the backflow section in there really to highlight the importance of you being aware of it. I'm not going to go into the code and I'm not going to talk about it all, but you know, residentially we don't see it as much now, but a lot of people would remove the backflow prevention device from a residential irrigation system to try and save the $37 that it costs to put it in there. And it's really the worst possible thing you could remove. Like, you're better off removing a sprinkler and letting your lawn die a little bit rather than removing a backflow and letting one of your family members die a little bit. Like, I know that sounds very dramatic, but we're spraying glyphosates and, you know, fertilizers and chemicals, and there's, you know, a lot of people using parks and gardens at night that may live there, and that who knows what they're putting on the sprinklers, but there's a lot of risk there. So it's really important to stay across your backflow prevention requirements. And if you're not sure, there's obviously a link there somewhere, to the SA government website around backflow. Backflow prevention devices do need to be installed by a licensed plumber, and then they need to be tested regularly. So that's, you know, good recurring business. I'm not sure if you've got plumbers working in. Do you guys have plumbers working? Yep. So can you test backflow? No. Yeah, perfect. Yeah, so then that's good recurring business. You can go out there, install the system, sign off on it, and then every 2 years, yeah, wicked. So when we do an irrigation design, we require a few things. Obviously, we require the area that we're irrigating. We require the specification. So we've just talked about that specification. I might write this down as I'm doing it, actually. So we need the flow and the pressure, or the flow versus pressure. We need the area. We need the spec, and then, you know, what they want to do. So if we're doing a job for, we'll go to Mount Barker this time because I've said Playford enough. So we're doing some work for the city of Mount Barker. We might have a council or a specification, which they do, and then we'll have a landscaper that's asked us to do a design and construct because they're going to be doing the work. We occasionally get engaged to go do a pressure versus flow test on behalf of our commercial clients so that you guys don't need to do it, whether or not it saves time. Obviously, it's a third party doing the pressure versus flow test, so the burden of it being right falls back on us. So we'll go do a pressure versus flow test. We use our GPS unit to do a walk around of the area, so we know exactly what we're looking at from where's the oval start and finish, where are the garden beds going to be. Obviously, if that area hasn't been built yet, then we'll rely on landscape architects' plans for us to design around that. We'll obviously look at the specification, and then we'll start the irrigation design process. The one thing that's not clearly outlined initially is the pressure versus flow test. So we've got these test kits that we use and hire and lend. This is by no means a sales thing. Most commercial businesses would have a version of this in their business already. So we would use this to test the flow and the pressure. Actually, I probably should go lower, shouldn't I? I keep forgetting about my cameras. So there's a video link there on how to do a flow test. We've got a lot of these kind of little how-to videos on YouTube, and really this is probably a good point to remind. Most cases, you'll be able to find the solution to what you're looking for on YouTube. It's the same as being at home and trying to fix a seal on a door or adjust a sprinkler. If you Google it, you'll find it. So this is our pressure versus flow test. You can mount this. What we would look for from you as a client is a static pressure, which is the pressure when the water's not flowing. So we would connect this to a water source and turn the valve off and look at the pressure, which is a no flow pressure. Am I moving? Should I be moving? And then what we would look for is a flow at pressure. So we've got here a digital gauge. So this will measure the litres per minute that are flowing through the gauge and just show the number so you don't have to measure it. Traditionally, for a residential irrigation system, we'd turn the tap on and then put a bucket underneath it and time how long it takes and then reverse engineer it. We don't need to do that now. So what we would look for is, say, a flow at maybe 300 kPa, 400 kPa and 500 kPa, and it depends on what the static is as to how high we can go. And then we would ask our client to kind of map it, or we'd bring it back. So we might have a pressure, so we'd have a 200 kPa, a 300 kPa, and a 400 kPa, and we might have, so static might be, say, 660. So what we would do is we'd open up that valve until the pressure gauge dropped to 400, and then we'd measure the flow that's coming out at 400, and we'd take record of that, and then we'd keep opening that and let the pressure down even more, so the gauge would go down to 300, and we'd measure the flow for that, and then we'd do the same for 200. And it would really depend on what the static is as to how much we can get. And the issue, I guess, when we're looking at static pressure, if we start getting statics that are below like usable water pressure, we're kind of stuffed before we begin, and we're at the situation where we'd need to then look at installing a pump, which might not be something that you guys have thought about. So what you'll find is those flow rates will change as they go. Like, we'll open it and get to 400. We might get 60 litres a minute coming out. We might go to 300 and get 80 litres, and we might go to 200 and go to 100 litres. So the more we're opening that up, the more water's coming out in litres per minute, but the less pressure, it's at a different pressure. And that's important to know for a lot of people that are beginning in irrigation. They're not aware that there's a difference between pressure and flow, and sprinklers require both numbers. Well, both numbers are important, so you'll find that you need a certain litres per minute with a certain pressure for a sprinkler to pop up and operate. If we were getting static pressures below 440 for that number, that's when we'd probably start having a conversation about putting a tank and a pump in. A sprinkler is going to need 350, and so with pressure, that 440, we start getting losses through things like backflow. So that's a backflow prevention device, which is what I was talking about before. You might lose 50 kPa through this, and it varies depending on the backflow, and all that data is available on the product information sheets that come with these. But yeah, once we get below 440, we're really putting in a tank and a pump, and in a lot of cases the flow's enough, so we might be getting 120 litres a minute, but at 200 kPa. So we can put a small tank in, have the 120 litres a minute fall into the tank, have a pump in the tank that's pushing the water out at the same speed, but at a higher pressure. So you don't necessarily need to have a 40,000 litre tank, and sometimes you might need to. Sometimes you can have a 5,000 litre tank, and all it's doing is taking the water that's low pressure at the right flow and pumping it out at the right pressure at the right flow. Does that make sense? Yep. If not, I can talk about that again in more detail after. Your face is saying, no, it's all good. I guess the key thing with this is for you to have an understanding of all of the micro things that are involved, but not necessarily have to remember them all today, and not necessarily, like obviously over time you're going to need to know it all, but it's really important just to get the idea behind today is to get a high level understanding of irrigation so that when you see something you go, hang on a sec, that doesn't seem right. Like I remember Clint talking about static pressure and the 400 or 400 or something. So if you do a pressure versus flow test with this and you test the static and it's 400 and something, that might be a phone call to Waterpro to say, hey, is this a problem? Like, should we be thinking about this? And we might be able to go, no, it's all good. You're running drip tube on the whole thing. Drip tube requires less pressure than sprinklers. It's fine. We've already taken it into account, but at least you've got enough of a base level knowledge of the things. Same with the backflow. I talked about that before. You know, if you're on a site and even a site that something doesn't make sense, right? Like there's water's not coming out over there when it should be. You go, where's the backflow? Because every site should have one. And then they're like, oh, we don't think there is one. Okay, well, that's a problem. So did we connect to the main line, or where did we connect this water in? So it's about kind of understanding all those small things and then knowing who to ask when you hit a wall. Our team are here to support you, and you know, I guess eventually they'll get frustrated by the same questions, but you can probably get away with it 5 or 6 times before they get really frustrated. The reality is we're a business that sells irrigation, and if we don't sell irrigation, we don't make money. If we don't make money, we don't pay our staff. So the more irrigation we sell, the better we're going to be. And the better you are at installing irrigation and the more comfortable you are installing irrigation, the more irrigation you're going to install. Makes sense. So I have no problem helping. That's getting really windy. And I have no problem with my team spending time. I mean, we don't charge for these trainings. We're getting offered money to do them. I feel like, I guess 2 sides. I feel like I probably have to deliver better quality training if I'm charging for it. But also, I feel like it's part of our relationship with you as a client to provide the training. So that's why we do it whenever we get asked. All right, I'm going to talk about precipitation next. We need to talk about scaled plans. Can you throw the plan up on the screen, please, Dill? All right, so now we're at the point where we've kind of we're on site now. So you guys have got a new job. You've just been given from whoever gives you jobs in your business. And they've said, here's a plan. Here's all the irrigation. Go install it, right? So these plans are all scaled, which means that if you have you've got a scale bar down the bottom, and then you'll be able to work out the length of things from that. There could be a potential that you were asked to estimate the job from this plan. The first thing you want to be doing is checking that scale is correct, because sometimes it's not. And you know, these irrigation designs, whether or not they're done by us or one of our competitors, are done by humans, and humans make mistakes. So the first thing that I encourage my team to do is check that the scale is correct by referencing it off of something. Now, obviously, this is on the planet Earth. You'll be able to kind of measure a lake or a car park or something and reference that against the scale to make sure it's right. And then, you know, that's the kind of first step of that. We design in color a lot now, and it's not something that was probably done 10 years ago, maybe a bit longer now, but for anyone that was doing irrigation installs 10 years or more ago, you weren't having, you know, colored drip valves. And so if you had a black and white printed plan, it could quite often be confused and you wouldn't know which pocket of drip tube was coming off of which valve. I would encourage you to print all of your plans in color, or at least check that there is no color referencing on them before you get started. Otherwise, you might find yourself getting in trouble for, I guess, putting the wrong thing in the right area. And then obviously, is this the correct revision? We've had situations recently where at tender stage, you'll have revision whatever, so revision 1, and then the landscape plans will change, and then revision 2 comes out, but we don't get given revision 2, but we've supplied it based on revision 1. And obviously that, you know, it becomes a bit of a situation of who's at fault, and obviously, you know, you don't want to get caught in a situation where you're having a blame game, but it happens. So I guess on that, I would encourage you to all do a pressure versus flow test on your sites before you start installing, and see that it matches up with the, where's that PDF gone? So most companies will put a section on here around the pressure versus flow. So we've got our system duty up here. I know you probably can't see it, but I think it says 46 litres a minute at 300 and something, 85 kPa. I guess when something goes wrong on site, there's two sides to it. There's one, let's fix it, and there's the other, who we're going to blame. And I think the best way to avoid the who we're going to blame, or maybe let's fix, probably both of them, is to find these situations before they happen. So if there's a system duty issue and the water flow will not do what it needs to do, so you think we've designed this irrigation system based on numbers that we understand are correct, and then something's changed on site. There's been a bunch of houses built behind there that, you know, the water authority has dropped the pressure because they're getting too many water bursts. A new school's been built and the water's, like, there's lots of things that can affect the flow. If you do a pressure versus flow test at the time of install, before you start digging up any ground, it gives you an opportunity as a contractor to go back to either the designer, the landscape architect, or the client and say, something's changed. Do you want us to just stick it in and you're going to pay for a system that doesn't work, or do you want to redesign it, or do you want to put a tank in, or how do you want to handle it? Because when we quoted the job, we quoted it based on the design. The flow doesn't match that design now, and we've had situations where the council will say, oh yeah, we probably didn't take that into consideration. We're happy to get a variation for a tank and a pump. Obviously that gives you more work as a contractor, but it also ensures that the system's going to actually work. So I would encourage you, once you get those plans, to kind of check over those dot points that I've put there before you start installing the job, and really, you know, almost counterintuitively read the instructions before you start putting the shelves together, kind of thing. And I know for me that's not something that I would usually do, but you almost start building this in your head before you start digging trenches, because it's very easy for our design team to draw a line on a piece of paper. Like, it takes them half a second, but that same line might take you half a day. And, you know, if you can pick up on issues that you might see arising before you start, or even suggested changes, we're not closed off to the concept of making changes around our designs or improvements around our designs. Like, if you say, look, it doesn't make sense that the main line goes all the way down there, can we just shorten it 20 meters? It's less than a roll, then there's a commercial implication to that. Like, we don't have to buy a 500 meter roll of cable, we can buy a 100 meter roll of cable. You know, we're open to that, and if we can take that back to your client and say, look, we've redesigned it with a shorter main line, are you happy with it? They'll be like, yeah, that's fine, that makes sense. Like, you know, they'll probably want some money for it, but, you know, we'll use different reasons. So I'll talk briefly about precipitation. All of this, kind of get your spec, get your plan. The designers are working on really effectively trying to mirror rainfall in an area. So obviously, if it rained every day for 5 mil of equivalent rainfall on every area, we wouldn't need irrigation. It's not the case, and obviously here in South Australia we go for long periods of time without rainfall. So what we're doing as an irrigation design company, and then obviously you as an installer, is trying to simulate even rainfall over lawns and gardens. Now, there's a couple of areas in there. There's a bunch of information around, you know, what Hunter's definition of precipitation is, and then I think there was a link to Wikipedia's. The simplest way that I can explain it is pretty much what I said before. You know, we are simulating rainfall using hardware and, you know, mains water in most cases. And what will happen is every sprinkler, or every product has a different precipitation rate. So this is probably going to start needing writing, I think. So if you're dealing with a professional irrigation shop, even some of the unprofessional ones, they'll be buying products from you know, world-renowned manufacturers, and most of those manufacturers have data attached to their products. So, you know, all the drip tube you see behind me has pressure-regulated drippers. They deliver 1.6 litres per hour per dripper out of the dripper. You know, the sprinklers that you buy, there's nozzle charts on how far the sprinkler throws, how much water it needs, and how many millimeters of equivalent rainfall that sprinkler might deliver if it's installed in the correct way. Mudge, can you get some MP rotator charts, please? So it's not likely that, sorry, that's probably not a good sentence. It's probably less likely that you're installing MP rotators on commercial sites than you would be on residential sites. But the MP rotator is a really good sprinkler for me to use to explain precipitation because you don't, like the design team, don't need to kind of make adjustments around where the sprinklers go from a half circle, quarter circle, full circle standpoint to be able to get matched precipitation. But the idea at an irrigation design level is that we plot out a hardware location for you that ensures that no matter where if you just want to just give a few out just so I can kind of use them to reference. The idea should be that any area of garden and any area of lawn gets exactly the same amount of water delivered to it as any other area of lawn and any other area of garden. So the way we do that with drip tube is by putting drip tube equally spaced over a whole area. So in South Australia, drip tubes installed at 0.4, 0.4, 1.6 a lot. And so there'll be a dripper every 400 in all directions, right? And they're 1.6 litres per hour, 0.4 by 0.4. So when we install drip tube at 400 mil spacing that way, and the drip is 400 mil apart, and use a 1.6 litre per hour dripper, that area gets 10 mil of equivalent rainfall per square metre per hour. And that's important because we can use that information then to understand scheduling, and then the councils can use that information to be able to work out watering budgets and when they're going to be watering and watering windows, and all of that's really important, and I'll talk about that. If you start putting drip tube closer together, so 0.3, 0.3 or 0.3, 0.4, that number, so that's 10 mil, goes up to 13, then up to 17. So if you're doing 0.3, 0.3, it's kind of 17.6 mil recurring, which is too much water in some cases for the soil profile to take. So we're thinking about how much water the soil can take when we're designing these systems as well. And that's why when you look in the Playford spec, you'll see that it's 0.4, 0.4, 1.6. It makes it very easy for them because 10 is such an easy number to schedule and an easy number for them to divide on site. And you'll see, can you bring that plan up again, Kira? You might start to see on more plans now, but we do it on their plans definitely. And can you zoom in on that table, please? Up here, we actually have, is it there? What's that asterisk mean? Usually, we will have the number of minutes required to deliver 10 mil. And I'm thinking that's what that number is. Yeah, that would make sense because the drip tube is 60 minutes. So Playford asked for that. They want that information so that they can reverse engineer what their desire. So they've got IPOS. Obviously, there's a standard that is designed to be met to keep turf at a certain level. So if you're an A-grade cricket field pitch or a footy field, they might say that needs to be IPOS level whatever. And to do that, you need to deliver 25 mil of equivalent rainfall to every square metre every week for that lawn to grow to that condition under normal weather conditions, which might be 30 degrees Celsius. And then they scale that up and down depending on it getting too hot or if rain events occur. So if that was the case for garden and they needed to deliver 25 mil a week, they know that they've got 10 mil per hour on irrigation, so they need to just multiply or divide that 25 by 10, and then they work out that they've got to do 2.5 hours of irrigation over the week, and then it really comes down to the council understanding when they want that to happen. And obviously, you don't want to do that every day and have kind of micro watering events because you really want to encourage deep root watering. So we might divide that into 2 1.25 hour waterings, 3 to 4 days apart, with the idea that the water gets deep into the soil to encourage root growth, which is not really anything that we take into account because the scheduling occurs after our life or after Waterpro have been involved. But there are situations, golf courses especially, where if we design a system incorrectly, there may not be enough hours in a week for them to apply enough water in a week for the lawn to grow, because there's golfers out at 6:30 in the morning, and then there's maybe weddings on at night, and if they can't get all their water out in the right amount of time, then they need to start thinking about adding rainwater tanks. So this is what a lot of golf courses do now. They'll have 500,000 to 1 million litres of rainwater tank storage, and then they'll use pumps to be able to get as much water out onto those areas as possible before a golfer might be on site, or even the maintenance team have to mow lawns. We'll see it a lot with the foreshore with Charles Sturt, so kind of Henley and Grange. They have people there doing yoga at 5 in the morning and people walking home from dinner at 10 at night. So they're watering windows even smaller than a golf course. All this information gets taken into account when they're scheduling to make sure that they can achieve the watering that they need to achieve to make sure that things grow. So obviously I've talked about drip tube. There's a little table there on page 10 around the precipitation, the cost per square metre, and then the flow rate. It's all connected, right? So the lower the precipitation, the more area we can water in one period, right? So MP rotators are a low flow nozzle because you can get lots of them on one valve at once. The issue with that is they are a low flow nozzle, so they're low precip, so they only deliver 10 mil an hour. So if you needed to get lots of water out in a hurry, they can't do that. They can only do 10 mil. Whereas if you start looking at 8005 gear drives, which you guys would have installed at some point, I'm guessing, these can get a lot of water out fast. The issue with that is you might only be able to put 3 sprinklers on one valve. So then you have to try and make sure that you can get all of those valves to operate inside a watering window, which for Adelaide City Council during Fringe, maybe not Fringe because they closed the whole thing down, but for those parks, those parks are getting used all the time. So they have to make sure that they fit that into their window. So I'll just draw the reason behind what I'm talking about with MP rotators. So when you have a basic square, let's say 4 meters by 4 meters, it's probably 4.1. We can put an MP rotator in each corner, and all they'll do is they just go head to head on each sprinkler. And we don't need to put, say, these two on for a different amount of time to these two. They can all go on at the same time, and they're designed to match. So when I'm talking about match precipitation, we could put a catch can anywhere on this lawn, and the amount of water that falls into that plastic can will be equivalent to the amount of water that falls into that plastic can, and so on. And that's what councils will ask us to audit when we're going out and checking irrigation systems that you may have installed. So if you've done a footy oval or even just a local park, there'll be a desired distribution uniformity, which is, I guess, the inconsistency between these catch cans needs to be at a certain level. The reality is it's never going to be 100%. We would go out and audit a system that's not, that hasn't been installed badly. It's just old, and there's sprinklers that might be tilted, or they might be cracked, or the nozzles have been drilled out to get more water out, or any number of stupid things. And the distribution uniformity might be 40 or 50%. The council might be happy with you getting it up to 75. And so the council will say, look, if you can get above 75, and I'd say, I don't know what Playford are going to do, but I'm going to guess it'll probably be closer to 80. They're going to say that we want an 80% DU to be met on these 3 areas once you finish the job. And they're not doing this yet. This is just what I can see coming. We would go out and do a catch can test. You could do your own catch can tests to try and check your DUs before you hand the job over, and then obviously pick up any potential issues before they arise. Put your cans out, you run your sprinklers for, say, 15 minutes, and then you measure all the volumes, and then you can put them into an Excel spreadsheet. It'll spit out a number and say, look, your DU's this area here is an issue, because they might be, they'll have numbers of mils in them, so they might all be consistent except for here, and that it'll be visually obvious because that sprinkler's tilted, or it's not turning, or the water's just falling out of it. So, and you might be able to see that before you even do the test. The idea behind the test is that they've got something physical from a data standpoint that the council can use to take back to you and say, you need to rectify this, there's a problem. When we do ovals, we don't use MP rotators. So a lot of the matched precipitation needs to be taken into account by our design team. And an oval is probably not a hard one to do because you're kind of just running sprinklers. You know, this is not by any means a great design. I'm just trying to highlight to you that when we have sprinklers on the outside of an oval, they're generally just doing 180. And when we've got sprinklers in the middle of an oval, they're doing 360s. We would either nozzle down these ones, so we would have a lower flow nozzle on the outside. Sorry, a higher flow nozzle on the outside, because they're going over the same area twice for every time. Is that right? Did I say that right? Lower flow, yeah, because they're passing over the same area twice for every one of that. Or they all have the same nozzles, but the sprinklers on the outside of the oval are on their own valve, and they water for less time, sorry. I got back from 7 days in Fiji yesterday and I'm a little bit doughy still. More doughy than normal. So we take care of that at design level. You shouldn't have to worry about it, but I think it's important for you to understand it so that, you know, I know that guys that are doing enough of this, they'll look at the plan and go, hang on a sec, why are those nozzles the same as those nozzles but the recommended run times haven't changed? Or why is that sprinkler on the same station as that? So we've got a full circle and a half circle on the same valve, but the designer hasn't nozzled them down to make that work. That doesn't make sense. So you can kind of go back to your designers and go, look, was this just a mistake or was it overlooked? And there might be a reason. They might say, no, those outside sprinklers are actually running 360. They want to water the outer even more. So just thanks for asking, but no, it's all good kind of thing. And so that will give you a precipitation rate. Now, I don't even know off the top of my head, but you might find that these 8 doubles might be closer to 25 or 40 mil an hour. That's you? Oh, you're going to talk? Talk.
Every now and then you'll find like ovals where they're really, really wet on the outer. And that's probably due to what Clint's saying, is they're just not nozzled down and they're just watering double the amount than what everything else is. So yeah, when you go to those ovals and they're just trashed on those outer rims, that's probably why. It's just getting double the amount and it doesn't need it.
All right, so that's all right. I just want to make sure I want to make sure I cover everything off, and I really want to. I want to make sure that you leave here with something that you can use that's real world, and it, you know, like it's this time of year. You're all very busy, and you know, for your managers and owners to send you here, I don't want that time to be wasted. All right, so that's designed, drip. Talked about drip tube. Does everyone understand? I can talk about how we calculate that if you want, because it's a pretty simple calculation, and it can be done a bunch of different ways. But ultimately, if you divide the number of square meters by the spacing of the drip tube, or like the spacing that you're putting the drip tubes apart. So if it was 100 square meters at 0.4, you can divide the 100 by 0.4, you'll get 250. So that's how many meters of drip tube would be required for 100 square meters of area. And then if you divide it again by 0.4, you get 625. That's the number of drippers that would be in the area. And then you times that by 1.6, which is 10,000. Times by 1.6 equals 10,000. Is that right? That's weird. Which is the number of litres that's going to get delivered every hour in the 100 square meters. So that's how we get our precip. So 1 millimeter of rainfall is 1 litre of water for every 1 square meter of area. Yeah? I'm probably jumping around a bit because that's how my brain works, but 1 mil is equal to 1 litre per 1 square metre. That's important to remember. You can use that when working out the size of a rainwater tank that you might be able to have at home based on the size of a roof of a shed, because you know that in the heaviest rain that you might have in a winter period is 100 mil a month, and so you can times your square meters of your roof by 100, and that you work out how many liters you get for every mil of rain you get. Because sometimes people will put a rainwater tank in at their house that's too big, and their roof is not big enough that it will ever fill that tank because there's not enough rainfall in the area. And sometimes people will put in rainwater tanks that are too small, expecting that they can water a whole lawn for the whole month or a whole year from a 1,000 litre rainwater tank. So we know this is a 10 mil per hour of rainfall kind of thing. That's a 16 square metre lawn. So you've got 160 litres per hour of watering. So with a standard 1,000 litre rainwater tank, that lawn is going to get 6 hours of watering, and that's done. So this is the beautiful thing about the science of what we do is everything that we sell and everything that you use and everything that you install has data behind it that enables you to work out the theoretical way that it's going to work before you start doing it. And by doing that, if we do everything that we said, so you check your flow versus pressure before you start, you check your scale on your plan before you start, all the pipe is the right size, everything goes in as per the design, it will just work. And when it doesn't work, there's a reason. It's not a case of, it wasn't just like, it was close or we hoped that it was going to work. Hunter sprinklers, sometimes it's 40 mil, sometimes it's 36 mil. It's not the case. It is what it is. It's hydraulically connected back, like it's all connected to itself. And so you can know that if you've checked that water flow versus pressure and you install things properly, it will work. And it kind of, the events of it not working are very low. And I guess then we start to understand when it doesn't work, it's because someone's put a solenoid valve in backwards, or it's been, the mainline pipe's been undersized, or I don't know, there's rocks in sprinklers, or flow controls haven't been open.
Going back to the drip and how Clint just sort of worked that out, that's how councils want to do it. They want to have that standard, right? So they know that they've got so many square metres of garden out there that they're delivering X. So when they turn it on for an hour or half an hour, they know they're putting out X. So that's why it's critical following the design for what Clint said as well, like right from the design part. So the systems, it is what it is, but also council know that, I should have put out X amount of water last night due to having X amount of dripper over X amount of square metres. Does that make sense? So, yeah.
The information that they take from that design then can get punched into central controllers. So obviously there's physical controllers on a lot of sites, but then a lot of those controllers connect back to a computer that they might have in their council offices, and they can make decisions around, or automated decisions around, sprinkler systems and drip tube systems not turning on because there's been a rain event of 12 mil or more or 8 mil or more. Sometimes, and they'll get a lot of shit for it because residents will say, why are you watering? It's raining. A lot of cases, the rainfall is not equivalent enough for the system to turn off. So, we're trying to put out, say, 12.5 mil on an oval because we've put some fertilizer out today and we really have to water it in, and there's a forecast of 3 mil of rain overnight. So we might do 9 mil, knowing that we've got 3. The danger is rainfall's generally theoretical. Well, it's theoretical at that point. Until we know that we've had 3 mil, we shouldn't really be adjusting the amount that's going out there, especially if we're applying a herbicide or a fertilizer, because if you don't put the right amount of irrigation out, you might burn the lawn, or it won't work properly. What time is it? So that's all pretty clear. All right, I'm going to talk about controllers next. What time is it? 2:45. I'll talk about controllers. I reckon we'll have a break at 3, and then we can kind of go from there. What time are you meant to finish work? That's right. I'll say you left at 4:30. What time? Yeah. I think we'll probably be done by 4. So I'll talk about controllers. So obviously, most of what we've talked about now has been around the actual products that deliver irrigation to the ground. So drip tube, sprinklers, that kind of thing. Really, there's, I guess, three ways we currently control irrigation systems or automatic irrigation systems. There's the traditional wired controller, which runs with a multi-core cable. There's the decoder controller, which runs with 2 core cable to decoders, and I'll talk about that in a sec. And then there's battery-operated solenoid systems, which is, your Hunter nodes. Obviously, each of those have pros and cons. The traditional irrigation controller, so the 240 volt mains wired controller, this is probably a decoder controller and I don't even know it. We'll call this one a 240 volt controller. So it plugs into a power point and then we run cable from that. The cable goes out to the solenoid valves and I'll talk about how that works after. Advantages, that controller gets plugged into a wall. You don't have to replace batteries. It should just work all the time. Obviously, when I'm comparing that to a battery-operated controller, batteries go flat. There's no Wi-Fi. Well, there is Wi-Fi, but there's not really Wi-Fi from battery-operated valves yet, whereas this can be connected to a SIM card. It can communicate back to base. It can be centralized, and there are ways to centralize battery-operated controllers, but it's quite new. And, once you've done that, and if you've done it properly, you shouldn't need to touch it again. Obviously, battery-operated controllers are going to need some form of maintenance. Battery technology is improving, and we're starting to see products come out now where the batteries are designed to last, 10 years? But these, they're running off 9 volts or AA's. They've started bringing out, I think the new Rainbird one's got AA's. AA's are meant to last longer. Yeah. So traditional controllers, when you've got, say, maybe 20 or 30 valves or less, makes a lot of sense because you can run cable out to them. So there's like a point where a decoder controller becomes more cost effective, and that's coming down. So I'll explain what a decoder controller is before I go too far into it, because some of you probably haven't even experienced that. But a traditional controller running from a 240 volt power plug has a transformer inside it that converts the electricity to 24 volt alternating current using a transformer. I don't think this is correct, but a transformer that would be down here. And then it travels out to the solenoid valves through cable. So you've all seen this cable. They come with single core, 3 core, 5 core, 7 core, 9 core, and 13 core. They're colored so that you can, I'm going to cut some off and sheath it. So they're colored so you can, which wire is going where. And what happens is this controller sends electricity down a common wire, and then the solenoid valve, so the active that's meant to be turning on, creates a circuit, opens the solenoid valve. Once we start getting up in the number of valves, it becomes challenging from an install standpoint because you've got these big looms of cable, but it's also quite expensive to be running. If you had 100 valves, you need 101 cables to go out through the whole area because you need one cable for every valve and the common to every valve. So there's a product called Decoder that is available in all the brands. And what that does is it's just a 2-wire path that goes to the whole area, and it sends out a signal to a decoder, which is like a translator box, really. I know that's a weird way of describing it. Have we got decoders here? Can you grab me one of them next? So what the controller will do is it'll send a signal out through the cable to say, decoder number 91648, turn on. And so that receiver translates that signal and opens the valve. The advantage of that is you're only sending 1 2-core cable out to the whole area, so you don't have these big looms of copper, which obviously there's risk of theft, and it's a challenging install, and it's quite costly. Obviously, the cost of copper is going up more and more. So once they get above a certain level, they'll go to decoder, and the the copper cost comes down, but then the actual cost of the hardware goes up because you're buying a decoder, which is that translator product for every solenoid valve. Decoders now cost, I don't know, I'm going to guess $100. Is a decoder $100? $130? Yeah, I don't know. I haven't worked in the shop for a long time. So these are the two cables. I'll pass these around just for anyone that hasn't seen them. I know there's a bunch of you that have seen these before. You want to see them? So you'll see the two wire paths quite thick. This is a residential cable, so this is a lot smaller than you'd be using on your sites. The decoder cable can go a lot further for a lot longer, so that cable there will go for kilometers, whereas the residential cable that they're holding up the front here is probably good for 100 to 120 meters before there's voltage drop, and there's some voltage drop charts in here on the next page. That's not a decoder, that's an RVM. Yeah, the decoder's like a toilet roll. So that's the decoder. This is a Hunter decoder. Obviously Rainbird have a decoder as well. The signal goes out through the two wire path. This translates the signal to on and off, turns the solenoid valve on. You'll notice there's copper here. These are quite sensitive to lightning. And one of the biggest risks you'll have with decoder controllers is the damage that can occur with lightning strikes. And so I talked about this right at the start about having the ohms resistance tests done on decoder systems. See the copper rods in the corner over there? They get used for lightning protection on these kind of systems. They'll get smacked in that deep, and then they have I don't even know what the product's called, like a gel set around them. The guys behind you can probably explain it better than I can. You install decoder systems, obviously? Yeah. So I've never installed one. I only know the theory of them. So the idea would be that if lightning hit the controller, any part of the cable, that the lightning would get grounded through those rods instead of frying these devices, which are worth $100 to $130 each. All of a sudden you've got, like I said before, you could have 100 on a system. It becomes a very, very, very expensive problem if your lightning protection hasn't been done properly. And that's why the councils are so insistent on checking that it's been done properly, because you could smack one of those rods into the ground, wire it up properly, put everything around it, and say, I've done everything I should have done. And then you do an ohms resistance test on there, and it's not your fault. You haven't done anything wrong. It's just the soil profile is so dry, or there's something that you didn't know that was there that causes it not to have good enough grounding, and then all of the work that you've done to try and ensure the system was wasted because of something. And, you know, I guess I don't know how you'd cross that bridge. Then you go back to the council and say, we've met the spec, we're not getting the resistance that you desire. What do you want to do? And in some cases, they'll put more, they might wet the area, or they'll put more of the product around, or they'll go deeper with the grounding. So, you know, they're the two hardware, I guess, the non-battery versions of control. And then we've got the Hunter node, which I'm guessing you guys have seen these. Yep. So you do like horticulture mainly. So like if you're doing maintenance on housing trusts, that kind of thing, you'll see these everywhere. It's really important to be aware that the polarity of these matters. So you'll see that there's a red and a black cable coming off of that solenoid valve. Other solenoid valves that are getting wired up to these controllers, so the traditional wire path, the polarity doesn't matter. So you'll find that there's two red cables. I don't have any solenoid valves here. So a traditionally wired solenoid valve like this, you got one there. Here's one I prepared earlier. So this is from our residential basics, but you'll see these two red cables are for a traditionally wired solenoid valve, so a cable to a controller. Because the 24 volt is alternating, it doesn't matter which wire goes to where. So when we wire these up to a controller, even a commercial controller, this is going to end badly, isn't it? You'll have a common here, and then master valve, and then you'll have 1, 2, 3, 4, and so on. So for a solenoid valve to operate, you have to have, for the traditionally wired solenoid valves, you need to have a circuit completed, which lifts electromagnetic pin in this coil, which changes the pressure in the valve and the valve opens. You can simulate that by turning the coil. So you'll notice sometimes people, if there's no power to the site, they can turn the coil a quarter turn or thereabouts, and it will actually open the valve. It's simulating the electrical process that turns the solenoid valve on and off. With the other one, the black and red cable, that's a 9-volt latching coil, so it actually sends through a pulse, latches it open, and then sends through a pulse to close it. So the polarity matters because it's not actually a continuous electric circuit that's holding the pin open. It's just a signal to open it and a signal to close it. So the decoder, where's the decoder? I don't know if it matters. Polarity, decoder runs to a DC coil. Do you know? I don't know. Does it? You think it does? I'm looking past you. You just worry about if that's zoomed in properly. What's that? Yeah, I'm just thinking, because decoder, the polarity does matter. Yeah, so I'll double check this because I don't want to give you the wrong information, but if you're using a decoder system, I believe you need to have a 9-volt latching coil. No, that wouldn't be right. Yeah, because it sends out a signal to turn it off and it sends out a signal to turn it off. So with a decoder system, like a golf course will use a decoder system because they might have, 15 solenoids open all at once. And their computer that they use to operate the golf course will learn the flow that is being used, and it will know, because obviously, as I said before, it's so important to have that watering window maximized. They'll say there's a green on the other side of the golf course that doesn't use much water. We're using, we've got, say, 500 litres wouldn't be that much. Could be 500 litres a second. Like there's some big flows going out of golf courses. We've got 100 litres a second still available. It's not being used. Let's turn on, T-block 5s, hole 5s T-block or hole 5s green alongside all the other ones. And then they'll turn them off and, the actual controller learns and will change its watering to meet the window rather than relying on the actual golf course superintendent or the irrigation team to do the programming themselves. All right. What I might do is take a 10-minute break now and just try and go through my notes and see what I've missed and make sure that I haven't missed anything, and then we'll come back and do some troubleshooting and some, I might do some hands-on stuff for the guys that actually haven't done it. I don't think I'm going to go past 4 anyway, but I just want to be conscious to respect your time and kind of make sure that we're finishing on time. So does anyone have any questions? Obviously, I've had a bit of a chance to talk to most of you during the break, but does anyone have any questions about anything we've talked about so far, or want me to kind of drill in more around, I don't know, how we calculate drip tube, precipitation, that kind of thing? If not, I can keep going. So I'll keep going with this. And then I think if we finish early or too early, for the guys that are, haven't done any irrigation, I might get out some poly pipe and some stuff, and we can, as basic as it sounds, do some repairs and that kind of thing. And if everyone else wants to stick around, they can. If not, I'll just tell your bosses that you left at 4:48 or something, and they're not watching this at all. So during the break, some of the guys that have had more experience with the irrigation, I was asking them, do you think there's much that I need to expand on? And we just briefly talked about the spacings of drip tube and how important it is to make sure that you are actually meeting the spacings that I had drawn up here before. And obviously, I explained why 0.4 matters. Recently, we've seen some work happening where the contractors in a rush, or they're trying to save costs. Ignore that. And there might be a garden area, and the drip tube is designed to be going every 400 for reasons that you understand now. And what they'll do is they'll just go like this, with the theory that that's good enough. All the plants will get watered. It's going to be okay. The issue you have there is that there's going to be inconsistent water being delivered in that area to that area, because obviously the drip tube's closer together, and then any plants planted along this area aren't going to get water. Beyond that, drip tube can't be run, so 13 mil drip tube, once it's run on its own for about 120 meters, water won't come out the other end. And so if you did that, and that was a 300 meter, or even a 200 meter, because it rolls 200 meters, if that was 200 meters, doesn't matter how much water you push into that tube, it's like trying to suck through a straw that's 200 meters long. There's too much friction and the water won't come out. And so that's why we have header pipes, which you'll see, from my little board before. So the header pipes that you can see connecting the drip tube, it's not just there to keep it neat. It actually provides a hydraulic purpose. And when you get really big jobs, those header pipes start pushing into 32 mil and even 40 mil PVC, because if you're looking at, say, a roadside, a highway project kind of thing, and it's quite thin, it's really long runs. What they'll do is we'll design, 100 meters of 32 or 40 mil PVC or even more, and it will have a bit pop out. So the water will come down one side. The valve will be here. That'll be quite large. And then there'll just be, 80 meter runs of drip tube coming off both ways. And the water gets delivered down that main pipe into there and then continues down into there. And that ensures that you're gonna get enough water delivery to those drip tubes and you don't have that friction loss. So friction loss is probably something that we talk more about in advanced irrigation when we, start to understand. Looks all right. Who made it? Who made it? Yeah. Friction loss is really important, and it's something that the design team take into account. You don't want water hammer, and if irrigation systems are designed where the pipes are too small, that's when you'll get hammer, and we try to keep the velocity down below a certain point, and then obviously that doesn't happen. So, if you see, I don't know, on a plan that someone's used 63 mil blue line and you're used to them using 50 mil PVC, they're actually the same thing internally. And if you feel like you can get away with 32 mil because it's worked on other jobs, but this plan says 40, don't mess around with it. We see it happen so much where even a solenoid valve, like we'll design a 25 mil solenoid valve going out to 63 mil blue line, which freaks people out because it's such a small valve up to a certain size pipe. But the flow is actually not that high. We just need to run that 63 mil so far away that we need 300 or 400 meters of 63 mil, so we're not getting friction loss down the other end of the pipe. So I never want to say that the design department anywhere are perfect and that you shouldn't question them. I just really want to highlight that most of the time the design's right. By all means, I'm happy for you to question our team. I don't know how other people feel about it, but I guess I wouldn't like to see you make a change around a valve without understanding why. We had a situation with one of the councils where we had a 25 mil solenoid valve going out to 63 mil. One of the guys that worked for the council knew more about irrigation than anyone I'd ever met in my life, and he decided that he wanted to put a 40 mil solenoid valve in because it fitted the visual of the 63 mil better. The issue was that there wasn't enough flow going into the solenoid valve to close it. So solenoid valves have minimum and maximum flows, which is data you can find out in Hunter books, Rainbird books. And so like a small solenoid valve, like these residential ones here, they need about 1.5 litres a minute for them to close. And you'll find if you do a residential courtyard and you've only got a couple of drippers on some pots, there's not enough water moving through the valve for it to shut. It will open, but it won't shut. So what happened in this situation is the valve that was at the start of that pipe was a master valve. And so no one will ever pick up on it. It just means that there's no master valve in play because there's not enough flow going through there for it to shut down, and you've kind of defeated the purpose of putting a master valve. All right, I think I covered off that drip tube. So while we're on the topic of master valves, commercially, these will be installed a lot. Residentially, not so much anymore, and I think we're probably part of the reason that they don't get installed. I just think that it's an additional cost that a lot of homeowners probably don't need to bear for a system where they're home most of the time. The idea behind a master valve is to have an additional layer of protection in front of all the other valves. So if this was I've done it too close. We'll say the water's coming in from this side. So on this system here, the master valve protects the manifold. It might not be obvious because my drawing's shocking, but that's a manifold. They're solenoid valves, that's cable, and that's a master valve. The idea behind a master valve is to, like I said before, to add an additional level of protection in front of these solenoid valves. So if one of these solenoid valves was to have an issue and it was leaking, that valve turns off when the system turns off, and it protects all of them. When we get to commercial applications, these controllers will learn how much flow passes through a solenoid valve during any cycle. And so if it knows that this valve delivers 112 litres a minute, and then all of a sudden 180 is flowing through the flow meter, it'll shut the master valve off because it knows that that valve's broken. Something's gone wrong. And so commercially now, a lot of systems will get installed with a flow meter. The way they're installed is really important. So you'll have specifications around the flow meter that they need a certain number of meters of pipe in front of the flow sensor, a certain number of meters of pipe after it, and obviously no bends and no joins. And have we got some flow meters here? Just if anyone wants to have a look. So you can get paddled flow meters like a paddle steamer. You can get lasered flow meters that measure the particles in the water as they pass by. There's a bunch of different ways to do it. This can also go to the level of if you had a property up the river and you were running off of a rainwater tank, or say not the river, say you had a rural property and the water that you had in your tank was the only water you had. If one of these goes wrong, you've lost your entire year's supply of drinking and showering and watering water. The master valve obviously helps protect it. If you don't have a flow sensor in play, you're not going to know that that's broken, except for the fact that, well, you just won't know. You'll find that you'll have two solenoid valves on at the same time. So what will happen is you turn your controller, the controller will turn valve number 1 on and it will start watering, but then there's water coming out of number 2 at the same time. So it'll only happen when the master valve's on. So you still need a level of maintenance there, but you'll find that you're protecting your water a bit more. Anyway, that's master valve. I'm going to have some of my coffee. He did a good job. So I want to talk about wiring up solenoid valves. The concept of solenoid valve wiring is the same. So that's just a water meter.
Yep. And that's a flow sensor.
And this is a flow sensor. So this is a kind of flow sensor that will measure, what camera am I on? That's a flow sensor that will measure the flow that's passing through the system while it's active. And that's the product that I was referring to that would understand how much theoretical flow there should be, and then if there's an actual flow variance, can turn the system off. This technology is available residentially now, so if you buy a Hunter HydroWise controller, you could fit a flow sensor residentially. It's not a cheap exercise, it's probably $1,000 on top of your system, but that will tell you how much water is being used, and you can then track that against how much you're meant to be using, and then obviously set some rules around turning the controller off at the master valve if you find that you're getting too much water. This is surprisingly good coffee. You make this? I've been having shitty coffee all week last week. So. Yep. So, question I was just asked was, when you say master valve, is that just a valve? So the answer is yes. In most cases, it's exactly the same valve that's here. But in certain cases, that valve might be, say, a Hunter ICV, and these might be Hunter PGVs. And so that one's rated to higher pressure than those, so that they're all protected from static, because you might have a really high static pressure, right? So if you had a house that had, say, 1100 kPa of static, or even 900, but when you turn the valve off, you get a spike of pressure, you could put a high pressure master valve here, and then you could put normal valves here. And so when that's shut off, none of that manifolding is under pressure. Because that's only rated to 1034 kPa. So if you want to protect it, you protect it there. Or you just have the same valve and it just becomes a secondary layer of protection, and it's fine. From a council standpoint, you'll see the master valve is not at the manifold like that. So can you bring that plan up again, please, Kira? See how quick she is. So if you have a look here, you've got your isolation valve. That's your main line. It connects in here. I don't think there is a master valve. You need to go up to the valve table. Oh, there is a master valve. Go down to the bottom, please. I can't find it. I think I should just go back to selling fertilizer. There should be a master valve there. There's a master valve in the table. Anyway, on a commercial system, the master valve's generally going to be at the start, and then obviously the solenoid valves get spaced on the main line. So you could imagine expanding this out to 100 meters of pipe, and then there's valves, you know, all the way along. A question I got asked in the break actually about decoders, and they are AC. Well, the Hunter to Hunter's AC. There's a lot of different variations with decoders. So there's now, Rainbird have got their IVM, which is DC, and I think they were saying you could use, say, a Hunter decoder with a Rainbird valve. It would have to be different, but these go in the valve box. So when you put the solenoid valve in the box, these are wired in that box, and they get grounded in the box. They don't sit back at the controller. They have to be at the valve. So I'm just going to show you how we would wire up a traditionally wired irrigation system using, so you guys had that colored cable before. So there's usually black, white, blue, green, yellow, red, brown. The colors kind of expand out as we get out to 13 core, but they always have a black and they always have a white in the 3 core. In Australia, the common cable, which is what I've got here, is C, is generally used black. And you know, a lot of the US comments on our videos on YouTube say that they use white. It doesn't really matter what you use for common. Obviously, I would encourage you to use black, being that it's pretty standard in Australia. I would also encourage you to use a common cable that's available in 3 core, because obviously that's the smallest cable you can buy. If you start trying to use yellow, then you have to buy, say, 5 core or 7 core for all your jobs, and it's inconsistent. The best thing about using a common cable and making it a certain color is that it becomes an industry standard. And this is the thing I was talking at the start about. There's like a lack of training and a lack of, like, I shouldn't be the one that's here telling you that common's black. I should hear that from Irrigation Australia, or, I don't know, the Prime Minister, who knows. But like, it shouldn't be me, right? There should be some kind of a standard, like there is with plumbing. Like, there's a standard, right? You meet the standard. So for the benefit of this, I would recommend that you use black for a common. So you'll have a cable coming out of the common port, and the common cable will go to one of every of the solenoid valve cables, right? So they're not 5 separate strands of cable. That's one cable that's getting linked in to each of the valves. So if you're looking at these, we're grabbing 2 of them. There might be 5. They all join together and they join to the black. Then the next cable, which is very likely to be white, and I don't have a white texture, might be the master valve, so that goes out to here. So every time the controller turns on, it sends electricity out of the common and out of one of the others. In this case, always the master valve, always the common. So then that'll complete the circuit of that solenoid valve, and it will open that valve. And then, say solenoid valve number 1, you'll join that up to the other cable, right? So you've got electricity coming out of the common and electricity coming out of port number 1, all while coming through C and M. So that's open and 1's open. Does that make sense? When we move to 2, that turns off. And then the cable that joins from 2 to there, the electricity is going through the common and out the 2, and it creates a circuit. It effectively switches on the solenoid valve. I don't have one. So when the electricity circuit's complete, there's an electromagnet that sits in the coil, ignoring that this coil's an AC coil, and it lifts the pin, and that's how the solenoid valve turns on. If you want to find more information about this, and I know you seem to be taking a lot of notes, you'll be able to find out a heap of this information on the internet if you want to do more education on it, or I'm happy to talk to you afterwards if you want to drill into it more. And obviously then you just work down the colors. So these are Hunter valves. They've got red cables. Rainbird valves have black cables. Old Philmac valves had white cables. It doesn't really matter what the color is that's coming out of the top of the solenoid valve if they're the same, right? So the fact that these are the same color tells me that it's an alternating current. The valve cable doesn't matter. It can be interchanged. It can be, if I had drawn that black line to that one instead of that one, and the green to that one instead of that one, it doesn't matter. Because the electricity is passing up and down, it's alternating. That's what AC stands for, alternating current. So you then obviously work your way down your colors. When I was installing a long, long time ago, I would work alphabetically with my cable and start with obviously black being the common, and then I'd go brown, LMNOPQ, yeah, blue, brown, and like I'd know the order of the colors. Again, that shouldn't be, that was just my standard, right? Because then I knew if I sent my team out to a site and they were like, it's the blue one, that was the valve 1 or valve 2 or whatever it was. I think you'll probably see standardization rolling out with this from Irrigation Australia in the coming decade maybe. But for now, I guess you won't find it in a spec. You might say use a black 2.5 mil or 4 mil common, like this, and then you might use your colored wires, but I don't remember ever seeing in a spec what color goes to what valve, and I don't know if you guys have ever seen that. What do you do? Do you just do you have a system you work through? Like I'm talking to the middle row. No? What about at the back? Do you have a color system or you just work through? Yeah, see how you think about how crazy that is, that being black, yeah. That feels like that standard has stuck. But you think like if you're going out, I mean it probably doesn't really matter, but it's just going to save time if you're troubleshooting a system and the blue is valve 1 or 2 or the red is valve 4, and you know, the challenge becomes a 20 valve system has 2 13 core cables running out to it. So there's 2 whites, there's 2 reds, there's 2 yellows, there's 2 browns, there's 2, anyway. I won't harp on about it. So that's how you wire up, I guess, the theory of wiring. If you are going to be doing irrigation regularly, I strongly encourage you to buy a set of quality wire strippers. The solenoid valves, we'll go through troubleshooting. Solenoid valves obviously require electricity and water to operate. If you have a situation where your electrical joins aren't done well and the solenoid valves aren't wired correctly, they might not turn on. If you have a situation where you haven't used waterproof gel connectors and water gets into the solenoid valve cables or to the joins, you might find that they fail and that they start to rust. A lot more detrimental to a decoder system than it is to a traditionally wired system, but it's not acceptable to twist wires together and wrap electrical tape around them and stick them in the ground and cross your fingers. Like there's, you know, wire joiner specifications, which will either be, these are the gold standard. They're a DBRY, so a direct bury silicon filled wire joiner. Yeah, we can get them. For those of you here today that haven't used these, I know that there's probably 6 of you at the back that have done more of these than I've even touched, let alone like need to have a practice shot. But if anyone here wants to have a shot with these, I'll explain how they work. There's a silicon or a gel inside these canisters. The red bit twists the wire together, and then the white bit keeps it waterproof. And so these, you know, will be used for decoder systems, and you can use them for, I wouldn't necessarily use them for residential systems because they're so big and they're quite expensive. But we've got wire field joiners that you can use for that. It doesn't matter what you do, unless there's a specification. I don't think it matters what you do to join your wires. You could solder your wires and put heat shrinks over them. You could twist them together and use these wire joiners. The main thing to be aware of is don't sheath your wire back past the joiner. So you don't want the wire joiner to finish and then there to be 2 or 3 mil of copper exposed because it can't get wet. It's really, really important that you maintain the integrity of the wire by it being completely sealed. It is very common for a valve box to fill up with water, and it doesn't have to be because the irrigation system's at fault. It could just be that it's been quite a wet winter and that water's in there. It could be that someone at council has turned on some sprinklers and forgotten about it. They're doing some testing and they've gone to have lunch. There's going to be water in the valve box. It's underground. So I can't stress how important it is to make sure your wire joiners are good. And it will be one of the first things that a consultant will check. So you think about, you've done a commercial project and I've come out and I'm like, take all your valve box lids off. Let's have a look. I can't see how you've glued PVC most of the time. I can't see how you've clipped up poly. I can't see a lot of things, but I can see your wire joins, and I can see your solenoid valves, and I can see your ball valves, and I can see how you've built your valve boxes. And this isn't designed for you to only concentrate on the things that people can see. It's designed to really highlight, I guess, how you do one thing is how you do everything. And if a consultant comes out and looks at your job and says, wow, like the valve boxes are straight, they're parallel or perpendicular to edges, they're all parallel to each other, the depths are consistent, the wire joiners are done correctly, there's no rubbish stuffed in the box, everything's been done right, you'll find that they're going to look at the rest of the system through a more rose-colored lens, and you might have less criticism around, I don't know, drip tube. They might dig up less drip tube to check that it's there. They might pop less sprinklers up because they start to get an understanding that the person that's installed or the people that have installed this project know what they're doing based on that kind of thing. So we can do some wire joining, like I said, for those of you that haven't done it. I want to talk through solenoid valve troubleshooting. So one of the more common questions that we get over the phone, mainly from homeowners, more so than landscapers, but sometimes landscapers, and I know I said this before and I mean it, if you're on site and you're struggling to work something out, by all means call us. And even, like I said, Mudge's cards are over there. Sometimes you've just looked at the same problem all day and you just need a second ear to talk to and go, hey man, I've done this, I've checked the wire joins, I've turned the water meter back on, the backflow's facing the right way, I don't understand why it's not popping up. And someone here will be like, oh, have you, is the solenoid coil damaged or something? And you're like, oh shit, I didn't even think about it. So I'll just talk through some solenoid valve troubleshooting for everyone. So as I said before, solenoid valves need electricity and water to operate. And so if they're not working, it's one of those two things. And what will happen with solenoid valves is they'll either get stuck on or they won't turn on. So I'll see if I can remember my table. So that with a solenoid valve, it either won't turn on or it won't turn off. So this is pretty much all there is, right? Electricity. So can anyone give me a suggestion why a solenoid valve wouldn't turn on based on water? Pressure. They do need minimum flows. One situation might be that there's no water. So either the backflow's backwards, the isolation valve's turned on, there's debris blocking water, the subdivision doesn't have water, could be a pump set that hasn't been installed yet. If there's no water coming into the solenoid valve, it won't turn on. It's very rare for it to be a pressure or a flow situation. Usually, because they require such low flow to open, they'll usually open. Yeah, that's probably it. So I'd be checking the backflow, isolation valve, could be a pump. So the pump might be plugged in but not turned on. And then the next thing, if you're trying to operate it automatically, and, oh, that's a wiring situation. I've given away the next one. All right, a water situation for why it wouldn't turn off. We just talked about it. Sorry, debris one, yep. So the debris, it's probably almost outside of both of them, but if there's a rock sitting in the solenoid valve stopping the solenoid diaphragm from closing, it's probably technically a water issue because it's not allowing the water to close it. Low flow. So if the flow rate is below the minimum, it won't shut off. If the solenoid valve's installed backwards, I'm pretty sure it will continue to let water through. What else? All right. Won't turn on. There's a heap of answers to this one. So if the wiring hasn't been done correctly, it won't turn on. If the controller's turned off at the power point, it won't turn on. If the controller hasn't been told to turn the valve on, it won't turn on. So especially with, like, I guess, dumb controllers that you can't actually physically see an app, or you're not looking at it at a computer screen, it can be quite confusing, especially for residential clients. They punch in all this information and it's kind of lost behind this screen, and all the information's here, and they're like, it didn't come on this morning. And then you're like, well, it wasn't meant to. You told it not to come on today because you've gone, don't water on Wednesdays or water every 4th day. So, I mean, that's an electrical issue. It's really a programming issue. What else is there? I think that's probably it. A break in the cable. So if you can't get electricity from the controller to the solenoid valve, like with a clean join, it won't turn on, right? It's sending power down that cable. It could be that you've wired it to the wrong coil. It could be that you've stuck the cable in the wrong port. There's a lot of troubleshoot. So the idea behind going through this today is that for anyone that's working at an entry-level irrigation role, this is probably the main thing you're going to come up against, is either the valve's not turning on or the valve's not turning off. And you're going to go to site with a 10-minute memory of this and a screwdriver and a key to a controller, and you're going to go, fuck, where do I start, right? Like, and the whole idea behind going through this is to go start with the least labor-intensive things first. So you go to the controller. Is it turned on at the power point? Yes. Go to the master valve or the backflow. Are they turned on, right? And start doing tests. So you might do a manual test on the coil. So rather than going and getting the multimeter out and testing things, you could just turn the coil. And if the coil opens the valve, then you're like, okay, so we've got water. Manually it works. We've got an electrical problem. And then you start chasing down the electrical problem. It won't turn off electrically. Really, the only real reason is because the controller's told it to stay on. And we get this with 4-station controllers running 4 programs. People go program 4 stations 4 times, and then they've got 16 watering events happening every 2 days, and they're like, my whole yard's flooded. I don't know what's going on. And then we start drilling into their controller, and they go, no, we've only got 4 stations. And I'm like, yeah, but you've programmed 4 programs on 4 stations, and you've kind of quadrupled your watering. So there's not really any other way, unless the controller freaks out and just dumps power down the lines, which is just, I've never heard of it happening, but they're the kind of situations that could occur. I don't know if it's more likely. I'd be interested to hear the input from the guys towards the back. If you have a solenoid valve fault, if you had 10, how many would be diaphragm and how many would be coil or power? Because my feeling is it's diaphragm more than coil. And I don't know, maybe on the older systems, the diaphragm's the thing that goes first. Is it 6-4, 5-5, 7-3 kind of thing? Yeah. I think I don't know, we sell more coils than, I don't know, I haven't worked in a shop for a while, but the reality is a solenoid valve, the designs of these haven't changed for 20 or 30 years. Like the Rickdell valve, which is, there's one, you've got one near Mudge. So that's a HR ripoff of the Rickdell valve. That's valve's been around longer than I've been around. Everything that operates is either non-frictionary or lubricated permanently. So there's nothing that can really go wrong unless there's like a external force, so a rock, debris, bad contracting, like, putting them in the wrong way. But diaphragms obviously tear over time, and coils can rust over time. The technology is getting, not when I say the technology, the designs of the coils are getting better and better all the time. Some of the old coils used to have a metal pin on the top that would rust and the coil would break down over that, but really there's not too much to them. And from my memory of working in the shops, it was such a regular occurrence that it was a solenoid valve that was keeping someone on site on a Friday afternoon at 4 o'clock more than anything else, like either not turning on or not turning off. And what really, like for those of us that do irrigation a lot, it's so simple. And it's like kind of, I keep referring to programming a VCR because I'm old now, but you get, at some point with irrigation, it'll just click and you'll go, I know it, right? Like there's kind of a finite amount of information that you can, I guess, if you understand 80% of what you need to know to understand everything, you'll understand more than most, because it's all those like kind of micro irrelevance kind of things around, I don't know, the things that pop up that my guys might see once every 10 years. You're just never ever going to come up against it. But if you can kind of understand that, you know, a controller is used as the brain and the clock to send electricity down to a solenoid valve, which is kind of the gate or the gatekeeper to the water. Then that opens and sends water down a piece of pipe, being it whether it's blue line, low density poly, PVC, copper, whatever it might be, out to the sprinklers or the drip tube. They operate. When that tells it to stop, the valves turn off and it stops. There's not much more to it. And then when something along in that, you know, that, I guess, skeleton or that ecosystem doesn't work, because you've seen it from such a high level, you're going, well, you actually start to synthesize the information really quickly, and all of a sudden you're like, well, I know that I need to start looking at this quadrant because it's a controller issue, because we've done this, or I know this, or I've seen that, or if the sprinklers aren't popping up, you know, you'll see it and you'll go, there's not enough water pressure. Why? And you start going back and going through, like, do we have to open up the flow control, or did we test the pressure versus flow before we installed it? No, we didn't. Okay, we probably should have done that. And it becomes quite simple. And I guess I see it quite simply, and I don't even do it. Like I just own the company that sells it now. But I think most of the guys will agree. Like there's probably more mystique around irrigation than there should be. And it's actually, you know, if you understand some real basic principles around scales and plans and flow and pressure and just meeting the specifications, you're not going to get into much trouble. I think it's when you start to try, I guess I say this a lot with other business stuff, learn the rules before you go to break the rules. Because once you know the rules, you know which ones you can bend and which ones you can break. And when I say break the rules, you might, instead of having a reducing joiner, you might have to make something by sticking a bush in a coupling. You know that it's not the exact fitting that should be there, but hydraulically it is not going to have a negative impact on the result of the job, and it's all you've got, and you're in the middle of nowhere and you need to get water back on because the family are trying to bath their kids, like that's fine. And so when I say break rules, I don't mean loop-de-loop drip line for 4,000 meters and then get out of there and hope no one notices, or, you know, using half mil cable just for that little bit because no one will notice on a commercial project. Like stuff like that can have an effect on the quality of a system, but if you do everything else kind of in line with those basic things, you're not going to get in trouble. And they're laughing because they've probably seen half of those things that I've just explained, but it happens, right? Like people try to save money and save time all the time, and then the reality is they, especially now, like there's more lens on irrigation than there ever has been before. All it's going to do is cost you, and I talked about this with Mudge before, and I forgot to tell you at the start, but you might feel like you're representing your business, and that if you leave, it's the business's reputation that gets left behind. But I can guarantee you, everyone in this little industry knows who you are as an individual. And if you do a great job, when I get a phone call to say, hey, did you ever know that person that worked at this company because they've just applied for a job? I'm like, yeah, they fucking did a great job when they were there. Why are they leaving? And they're like, oh, I just had an issue, whatever. People know what you're doing. And if you try and take those shortcuts, it follows you, especially, I mean, you guys, you know what Adelaide's like. And I don't want to sit on a high horse too much, but there's such a good opportunity for all of you as employees in your businesses in the irrigation field. It's an understaffed field. It's going to be, like water's, you know, our most precious resource, and there's not enough people coming through the junior ranks to be able to fill those roles. And if you get really, really good at this, you'll have a good job, if that's what you want, for as long as you want, in my opinion. So that's enough high horsing from me. There's a bit of stuff here about the install. Obviously, there's a commercial side to our business. We do sell irrigation. If you choose to work with Waterpro, and there's no, you know, just because you come and do a training session here doesn't mean you have to buy from us. It's not how I work. We can kind of customize the irrigation supply to how you like it. So we've got clients that will send a shipping container here, and we'll pack a commercial project into their container, and then the container will go, especially regional, like I think we've done it with you guys, like Whaler, or like there'll be job sites where that needs to happen, or they'll ring up and say we need cable, mainline, and valves, and we'll push that out, and then 2 weeks later they'll ask. And that's the advantage of this, obviously, the volume of stock that we hold here. We can hold, quite substantial projects without needing to send them straight out. The way people install irrigation systems kind of varies, and I'd be interested to hear from both companies. Some people like say you had an oval, some people like to do their laterals and work back to the valves and then work back down their main line, and some people like to work out their mainline cable and valves and in. Do you have a preference, or is it really job dependent? I'll ask outside first. Yeah. So if you don't have access to the oval, you might be sticking the mainline in. Yep. It's probably one of the beautiful things about irrigation is, I guess, unlike a house, you can't just put the roof on and then work your way down, right? But with irrigation, you could put the laterals, or you could do the drip in the garden bed that's finished and mulch it, and then work your way back to the valve, and then work your way down. And so there's no right or wrong with that, provided that you're meeting the specification. And I think it's important to highlight that for the guys here that haven't done it. You don't have to start by mounting a controller on the wall, because in a lot of cases there's no power and there's no wall. So you might go do the other things first and then work your way back, and that's fine. There's a note here about mainline pressure tests. It's one of the things that's getting done more regularly now, which obviously you guys would have seen, but you guys might not have seen. So when the job gets finished, before the end user, which is generally a council if they're doing a mainline pressure test, gets handed over, they'll come and actually pressurize the mainline, and it needs to stay at that pressure for a certain period of time. If it doesn't, it won't meet the expectations, and obviously there's a leak happening somewhere. Ball valves and manifolds, dual checks. There's a little bit here about, I'm not going to go into techniques, but I will stay here and talk to anyone that wants to look at a welder or talk about a thing, or glue some pipe or thread tape a fitting or whatever. Things to note: ball valves required on manifolds. Residentially and commercially, I really encourage you, it's going to be in the spec anyway, but usually there'll be an isolation valve here, or here, 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 and here. You don't want to have to isolate someone's house for a week to fix their irrigation system. You want to be able to just turn off the valve and isolate the system. You don't want to stop watering the rest of an oval while you fix the valve that's damaged on an oval. So it's good to have an isolation valve. So that's just a manual ball valve like that. So you can turn it off, especially if it's on a weekend. The person that's at the footy ground might be able to just turn the ball valve off, and then your crew can go out there and fix it on a Monday rather than getting called in on a weekend. Master valve we've talked about. We didn't really talk about pressure reduction and filtration. I might quickly go through that just for the people that haven't had a lot of experience with irrigation. So at the start we talked about static pressure, that kind of thing, right? So sprinklers are going to have a range of, say, 300 to 400 kPa, and that's not the exact range, but just for the benefit of this, that they want to operate at for them to pop up and accurately spread water. Whereas drip tube wants to sit in kind of a 150 to 210 kPa kind of place. The drip tube behind me, everything we sell is pressure compensated, which means it has a rubber diaphragm inside the dripper that regulates the amount of water that comes out each dripper, and that's how we get that 1.6 litres an hour at every dripper, and so that we can design a system that has matched precipitation. If there's too much pressure coming out of a solenoid valve, so if you think we've got 660 kPa here that goes through a backflow, so we'll say there's a backflow there, it becomes, say, 610, goes through a solenoid valve, becomes 590. These aren't exact numbers, but just work with me. And gets to the first valve. By the time it's coming out of this valve, it might be 580 kPa. That's too much pressure for drip tube, right? You want it to pressure down to 200. Say 25 PSI generally is 160. So what we do is we fit a pressure reducer. That's a pressure reducer, good work. We fit a pressure reducer to the solenoid valve to reduce the pressure here. So it passes through that pressure reducer, and then all the pressure that's going out to that drip tube is now reduced to a level where the rubber diaphragm that's actually regulating the flow, so the litres, not the pressure, it actually operates properly. If you have too much pressure coming out to a drip tube, the pressure compensator won't work properly, and you might find that it squeals. It's probably the two main things. I don't know how much damage it does. I don't think it does that much damage, but it's definitely best practice. And so you'll find commercial projects, they'll either have an AccuSync, which sits on the valve, or an OmniReg, which is it OmniReg? That's Toro's. I think Mudge is on Instagram or Tinder. Hey. Can you grab me like an AccuSync, please? So sprinklers aren't any different, but it's a lot less common to see pressure reduction on a sprinkler system. And especially in the world you guys live in, we're so starved for good pressure that it's very rare for us to get something so ridiculous coming into a sprinkler system that we have to reduce it. But there are situations when we might reduce the pressure back here and reduce the whole system, which is he had before. So this is an inline pressure reducer that can reduce the whole system. So you'll see these on new houses now. They're generally 500 kPa going into a house. That's designed to protect washing machines and dishwashers that are now manufactured that can't handle any higher pressures. Sometimes, if that's fitted, what a homeowner might do is take a main line from their water meter in front of this and send it to the back of their house, and so that they can lift the pressure that's going into the front yard and into the backyard, because 500's, 450 or 430 by the time it gets to the back, and then they're not popping up sprinklers. So these are all retrofittable pressure reducers that fit to solenoid valves, which might sound crazy because I still don't understand how they work, but you can screw that. Do you know how they work? I don't know how they work. They work. So you screw that to the solenoid valve under the coil. So you'd remove the coil, put this between the coil and the solenoid valve, and you can adjust the pressure of the valve with that. That's obviously, you need to go to uni for that one, but I don't know how it works. Do you know how it works? Yeah. So the reduction, from a sprinkler standpoint, there actually are pressure reducing bodies now. So you'll find that probably Playford again, instead of having pressure reduction at the valve, every single sprinkler will have a pressure reducer in it, which it's ridiculous from a cost standpoint. Like those sprinklers are what, $25 instead of $5, and there's hundreds of them. But that's what they want. I mean, it ensures that the match precipitation that we were talking about before works. And the thing is, we could do all this design and we leave the pressure reducers off at install, and then there's inconsistencies around how the water's delivered, and all of a sudden match precipitation's out the window, and we wasted all that time. So pressure reduction is very important. You want to make sure that you're getting the pressure required at each of the water delivery devices to make sure that they're working properly. In my opinion, filtration, not as much. Now, the caveat being, it depends on the quality of water, but we sell very little amounts of filtration devices directly off solenoid valves in the shop. Obviously, commercially, they'll be specified. What are they? They've got those Rainbird pressure reducer basket filters, like Playford love them. So they reduce the pressure and they filter the water. Great. The main reason I would suggest putting filtration into systems isn't so much to keep the water that's coming in normally clean. It's in the event that water gets dirty because a main line's been blown under a road, and while they fixed it, some rubble or some rocks have gotten into the system, and then it comes into your system, and then it damages something. But I don't know. I mean, I'm all about selling sprinklers and sprinkler systems, but I think that if you had to cut something, before I said don't cut your backflow, I'd cut my filter. But this is an all-in-one, so it's a filter and a pressure reducer all-in-one. So, I mean, I don't even know what they cost, but it's not, now that you can get two in one, you're almost paying for one, but you're getting two. Any questions about that? I've skimmed over that pretty fast, and pressure reduction is pretty important, but I am conscious that there's people that obviously do this every day, and then there's people that are still learning. So, does anyone have any questions? Everyone wants to go home? Okay, so Jen just asked, obviously we sell, 25 PSI, 30 PSI, 35 PSI, 50 PSI pressure reducers. And I've talked to you about KPA all day. The multiplier is 6.9 roughly. So obviously a 25 PSI times by 7 goes up to about 160 or 170 KPA. That's not the question you asked. The idea is that the pressure reducer that's getting installed has to be suitable for the product that it's sending water to, right? So if it's all flat, because elevation affects pressure. So if you, say, had a system that goes downhill 30 meters, you're having an extra 30 kPa of pressure added as it runs down the hill to the bottom. So you might find that we have to have a lower pressure reducer than we might think, because it's actually increasing as it goes down. Drip tube needs less pressure than sprinklers, so we might have a 25 PSI pressure reducer for drip tube because it sits inside the range. And if you actually go look at NetFM's website or any of the books, it'll say operating, ideal operating pressure 160 to 210 kPa or 160 to 190. All we're doing is trying to work out the most appropriate pressure reducer for that, keeping in mind all the variables. So once the water leaves the pressure reducer, it's still losing pressure. So you need to have enough pressure at the start of the station to get to the end of the station but stay inside that window, right? So with sprinklers, we know that we might need, say, 300 kPa for MP rotators. And that number might be wrong. You guys have got the charts, you'll be able to tell me. So you might put a 35 PSI or a 40 PSI pressure reducer, knowing that as it goes through, it's going to lose another whatever, and then they'll still sit inside that range. So that's how we that makes sense? Cool. I've sped through a lot of that. That is irrigation basics, and the idea was that you went away with a basic understanding. Obviously, more than half of you have more than a basic understanding. I do these all the time, but they're always different, and I guess it depends on the crowd. I kind of feed off of you guys to try and see what you need to know. So yeah, if there's more that you want to know, I'm happy to stay here until whenever and talk to you about irrigation till whenever. Obviously, as I said, they're recorded, so you can watch any one of them if that's the kind of thing that gets you off. We will do advanced irrigation training sessions, which won't be me, it'll be Matt. He's a lot smarter than I. And so we'll communicate with your businesses around that. It is my desire to have a proper setup to be able to do hands-on and have you glue stuff together and fix blowouts and troubleshoot cable. There's just a commercial reality to it that it's just going to cost me money to kind of do it, so I just have to work out how I'm going to do it. So thank you for coming. I appreciate it. I know that this is probably the worst time of year for you to be coming off of site and sitting here and doing education, but I do appreciate it. And yeah, like I said, if you've got any questions, I'm happy to stick around off camera and talk about it. Help yourself to some drinks and that, and grab his card if you want. But that's it. Thank you.